You already know that the universe is big. But here is the part that most people don't know. It is getting bigger. Right now. As you watch this. And not just bigger, it is getting bigger faster and faster every single second. Now here is the question. What is pushing everything apart? Gravity pulls things together. So what is doing the opposite? Scientists call that unknown thing dark energy. And today, we are going to understand exactly what that means, and why it is the biggest mystery in all of physics. Before we can understand dark energy, we need to understand the expanding universe. Let's build this idea from scratch. Imagine these dots are galaxies. Each one is sitting in space. Now watch what happens to the space between them. The galaxies are not flying through space. Space itself is stretching. That is a critical difference. The dots stay still, the fabric moves. Edwin Hubble discovered this in 1929. He noticed that almost every galaxy we could see was moving away from us. And the farther away a galaxy was, the faster it seemed to be moving. This pattern had only one explanation: space itself was expanding. Think of it like drawing dots on a balloon and then blowing it up. Every dot moves away from every other dot. No single dot is the center. So by the 1990s, scientists knew the universe was expanding. But they had a very clear prediction about what should happen next. Gravity, they said, must be slowing the expansion down. Think about throwing a ball upward. Gravity pulls it back. It slows down before it falls. The universe should be doing the same thing. The Big Bang gave it a push outward. Gravity should be pulling everything back, slowing the expansion over time. Scientists in 1998 set out to measure exactly how much the universe had slowed down. They were not asking if it had slowed, they were asking how much. What they found instead completely shocked them. And it changed physics forever. Two separate teams of astronomers were studying a special type of exploding star called a Type Ia supernova. These are important because they always explode with exactly the same brightness. Because the brightness is always the same, scientists can use supernovae as distance markers. If one looks dimmer, it is simply farther away. It is like using a known light bulb to measure how far away a room is. The teams measured supernovae that were billions of light years away. They expected to find them slightly brighter than predicted, meaning the universe had slowed down and those galaxies hadn't gone as far as feared. Instead, the supernovae were dimmer than predicted. Not brighter, dimmer. That meant they were farther away than expected. Farther away than expected means the universe had not slowed down. It had sped up. The expansion was accelerating. Both teams, working independently, found the same result. They double-checked everything. The answer was clear. The universe is expanding faster and faster. This discovery won the Nobel Prize in Physics in 2011. And it gave the mysterious force behind this acceleration a name: dark energy. Here is a common confusion. When scientists say dark, they do not mean it has a color. They do not mean it is scary or mysterious in the everyday sense. In physics, dark simply means we cannot detect it with light. We cannot see it. We cannot capture it with any telescope. It does not emit, absorb, or reflect light in any way. We only know dark energy exists because of what it does to the universe around it. We see its effects, not the thing itself. Like knowing the wind exists because you see leaves moving. This is actually quite normal in science. We cannot directly see gravity either. We only see what gravity does to objects around it. Here is something that might surprise you. If you took everything in the universe, every star, every planet, every atom, every force, and added it all up, dark energy makes up most of it. About 5% of the universe is ordinary matter. That is everything you can touch, see, or measure. Every star, planet, gas cloud, and atom. About 27% is dark matter. That is a separate mystery, invisible matter that holds galaxies together with gravity. We'll leave that for another video. The remaining 68%, the biggest slice by far, is dark energy. Most of the universe is made of something we have never directly detected. Think about that. Every telescope ever built, every lab ever created, every particle ever detected, that accounts for just 5% of what exists. So what is dark energy? Here is where it gets genuinely fascinating. The leading theory connects back to Albert Einstein, and a mistake he thought he had made. In 1917, Einstein was building his equations for how gravity shapes the universe. His equations kept producing an unstable result, a universe that either expanded or collapsed. But the science of that time said the universe was static, fixed in size, not growing or shrinking. So Einstein added a special term to his equations to hold the universe still. He called it the cosmological constant. The cosmological constant acted like a built-in repulsive force, something pushing outward against gravity to keep everything balanced. Then Hubble discovered the universe was expanding anyway. Einstein removed his constant, called it his greatest blunder, and moved on. But here is the twist. When scientists found the accelerating expansion in 1998, they realized Einstein's discarded cosmological constant might actually be the explanation. The cosmological constant today is interpreted as a property of space itself. Empty space has energy. That energy drives the expansion. Wait, empty space has energy. That sounds impossible. If space is empty, what could it possibly be made of? Quantum mechanics tells us something very surprising. True emptiness, zero energy, zero activity, is actually forbidden by the laws of physics. In any region of space, particles are constantly popping in and out of existence. They appear, interact, and vanish in an incredibly tiny fraction of a second. These are called virtual particles. They carry real energy. And because space is everywhere, this energy is everywhere too, spread uniformly across the entire universe. This is called vacuum energy or zero-point energy. And the exciting part is, quantum mechanics predicted this long before dark energy was discovered. The cosmological constant in Einstein's equations maps cleanly onto this idea of vacuum energy. Empty space pushes outward. And as the universe gets bigger, more space exists, and so the pushing gets stronger. Now, here is where science runs into a massive problem. Not a small one. One of the biggest mismatches in the history of physics. Quantum mechanics can calculate exactly how much vacuum energy empty space should contain. It gives a specific number. Astronomers can also measure how much dark energy the universe actually seems to contain, based on the expansion rate. The quantum prediction is 10 to the power of 120 times larger than the observed value. That is a 1 followed by 120 zeros. No measurement in science has ever been this wrong. This is called the vacuum catastrophe. And it tells us that while vacuum energy might be related to dark energy, they are probably not exactly the same thing. So the cosmological constant gives us a useful label for dark energy. But it does not fully explain it. We can describe what dark energy does. We still cannot explain what it fundamentally is. Because the cosmological constant doesn't fully satisfy physicists, some have proposed a different idea. What if dark energy is not a fixed property of space, but a dynamic field that changes over time? This idea is called quintessence. It comes from the ancient Greek concept of a fifth element, something beyond earth, water, fire, and air. In physics, quintessence would be a field, similar to electric or magnetic fields, spread across all of space. And unlike the cosmological constant, it can vary in strength at different times and places. Quintessence could explain why the expansion rate today differs from what it was billions of years ago. And it would mean dark energy is not permanent. It might weaken, or even reverse. But here is the problem. So far, all measurements of dark energy show it behaving like a constant, not changing. Quintessence is still a live theory. But the evidence isn't there yet. There is a third idea that is even more radical. What if dark energy doesn't exist at all? What if Einstein's theory of gravity is just slightly wrong? Einstein's theory of general relativity has passed every test we've thrown at it here on Earth and in our solar system. It is incredibly accurate at small and medium scales. But general relativity has never been tested across the full scale of the universe, billions of light years. What if it breaks down at those extreme distances? Some physicists have proposed modified gravity theories. These say that gravity behaves slightly differently over cosmic distances, naturally producing an effect that looks like acceleration. The problem is that modified gravity theories are very hard to make work. They explain dark energy, but often break something else, like how galaxies form or how light bends. Now let's talk about how scientists actually study dark energy. Since we can't detect it directly, we study its fingerprints, the patterns it leaves in the universe. The first method is the one we already discussed, type Ia supernovae. By measuring how bright these explosions appear from Earth, we can trace how fast the universe was expanding at different points in history. The second method uses the leftover glow from the Big Bang, called the cosmic microwave background. This ancient light carries a snapshot of the universe when it was only 380,000 years old. The third method is called baryon acoustic oscillations. Before the universe cooled, sound waves traveled through the hot plasma of the early universe, like ripples in a pond. By combining all three methods, supernovae, the CMB, and these acoustic oscillations, scientists have built a consistent picture of dark energy. And they all agree, 68% of the universe. Constant, pushing outward. Now here is the part that brings everything together. If dark energy keeps doing what it's doing, if the expansion keeps accelerating, what happens to the universe in the far future? First, and this is already happening, galaxies that are very far away are receding so fast that their light will never reach us. They are crossing what's called the cosmic horizon. Over billions of years, galaxy after galaxy will cross that horizon. Our night sky will slowly go dark. Galaxies we can see today will eventually vanish, not because they exploded, but because space stretched too fast for their light to ever reach us again. Eventually, trillions of years from now, stars will burn out. The last stars will go dark. The universe will enter what scientists call the degenerate era, then the black hole era. And then, if dark energy persists, even black holes will eventually evaporate through a process called Hawking radiation. And the universe will be left cold, dark, and empty. This is called the Big Freeze, or heat death of the universe. It is the most likely outcome if dark energy remains constant, which, right now, it appears to. But what if dark energy doesn't stay constant? What if quintessence is real, and the energy pushing the universe apart actually gets stronger over time? If that happens, the expansion could eventually become so fast that it overcomes not just the gravity holding galaxies together, but the forces holding atoms together. First, galaxy clusters would be ripped apart. Then individual galaxies. Then solar systems. Then planets. Then, in the final moments, even atoms themselves would be torn to pieces. This scenario is called the Big Rip. And it would happen at a specific moment, a calculable point in time, when the expansion rate becomes infinite. Right now, the evidence doesn't point to the Big Rip. Current measurements suggest dark energy is constant. But we can't be certain, which is exactly why scientists keep measuring. And there's a third possible future. What if dark energy weakens over time, or even flips direction and becomes attractive instead of repulsive? In that case, gravity would eventually win. The expansion would slow, stop, and reverse. The universe would begin contracting, collapsing inward on itself. As the universe contracts, galaxies would merge. Gas clouds would compress. Temperatures would skyrocket. Everything would come back together in a single catastrophic collapse. This is called the Big Crunch. And some physicists even wonder, could the Big Crunch then trigger a new Big Bang? Could the universe be cycling through expansions and contractions? We don't know. These are the open questions at the frontier of cosmology. The answer depends entirely on what dark energy actually is, which we still don't know. You might be wondering, if dark energy is 68% of the universe, Why is it so hard to study? Shouldn't something that dominant be easy to detect? The problem is that dark energy is spread incredibly thin. There is very little of it in any one place. It only becomes significant when you add up the contribution from the entire universe. For comparison, a single candle flame releases more energy per cubic meter per second than dark energy does across the same volume of space. Dark energy's power comes entirely from scale. Space is unimaginably vast. Add up that tiny contribution from every cubic meter across billions of light years, and you get a force that dominates the universe. This also means we can never build a dark energy detector in a lab. The scale needed to measure it meaningfully is the universe itself. Here is something exciting. The study of dark energy is accelerating, pun intended. Several major scientific missions are actively mapping it right now. The Dark Energy Spectroscopic Instrument, DESI, is the most ambitious galaxy survey ever built. It sits on a telescope in Arizona and can observe 5,000 galaxies simultaneously. DESI is creating a 3D map of the universe across 11 billion years of cosmic history. By tracking how galaxies are distributed, it measures the frozen ripples we discussed earlier, and uses them as a ruler to track expansion. In 2024, DESI released its first major results. And they were intriguing. They suggested that dark energy might not be perfectly constant. That it may have been slightly stronger in the past. This does not mean the cosmological constant is wrong. The variation is small, and the data needs more analysis. But it is exactly the kind of hint that could lead to a breakthrough. The Euclid Space Telescope, launched by the European Space Agency in 2023, is specifically designed to measure dark energy. It will map over 1 billion galaxies. Together, these missions will give us the most detailed picture yet of how dark energy behaves across cosmic time. By the 2030s, we may have answers that fundamentally change our understanding. Here is where dark energy becomes part of the biggest question in all of physics. Not just cosmology, but the entire foundation of how the universe works. We have two pillars of physics. General relativity describes gravity, space, and time, and works brilliantly at cosmic scales. Quantum mechanics describes particles and forces, and works brilliantly at atomic scales. The problem is that these two theories are fundamentally incompatible. When you try to apply both at once, in conditions like black holes or the Big Bang, the math breaks down completely. Dark energy sits right at this intersection. Understanding what it truly is may require a new theory, one that unifies gravity with quantum mechanics. We call this the search for quantum gravity. String theory, loop quantum gravity, and other frameworks all try to build this bridge. None have fully succeeded yet. But dark energy provides a test, a real cosmic measurement, that any successful theory must explain. Let's step back for a moment. Not just from dark energy, but from everything. Because there is a deeper story here, and it's worth hearing. For most of human history, we thought Earth was the center of everything. Then we learned it was just one planet around one star. Then we learned our star was just one of 200 to 400 billion in the Milky Way galaxy. And the Milky Way is one of at least 2 trillion galaxies in the observable universe. And now we know that all of that, every star, every galaxy, every atom of ordinary matter, makes up only 5% of what exists. We are a tiny island of light in an ocean of something unknown. This is not a reason to feel small or insignificant. It is the most exciting time in scientific history. We are the first generation of humans who even knows dark energy exists. Here is something that surprises a lot of students. Not knowing the answer isn't a failure in science. It's a tool. It tells you exactly where to look next. Dark energy is what scientists call an open problem. That means it's a real, confirmed phenomenon for which we do not yet have a satisfying explanation. Compare it to dark matter, which is another open problem. Or to turbulence in fluid dynamics. Or to the mechanism of general anesthesia. Science has many things we can describe perfectly, but not explain fundamentally. And that is what makes this the golden age of cosmology. Every measurement we take, every supernova mapped, every galaxy catalogued, could be the one that cracks it open. Scientists have a precise way of measuring how dark energy behaves, a number called the equation of state parameter, labeled simply as W. If W equals -1, dark energy behaves exactly like the cosmological constant. Fixed. Uniform. Not changing. That is the simplest possible dark energy. If W is greater than -1, say, -0.8, dark energy is weakening over time. The universe will eventually stop accelerating. This is the quintessence region. If W is less than -1, say, -1.2, dark energy is growing stronger. This leads toward the Big Rip. This region is called phantom energy. Current measurements of W from all our best telescopes place it very close to -1. Exactly where the cosmological constant predicts. But the error bars are still wide enough to allow some variation. Let's bring everything together now. Let's rebuild the full story of dark energy from the beginning, piece by piece. We started with Hubble discovering in 1929 that galaxies are moving apart. Space itself is stretching, not the galaxies moving through space. Scientists expected gravity to be slowing that expansion down. They measured supernovae to find out by how much. What they found in 1998 shocked everyone. The expansion was not slowing, it was speeding up. Accelerating. Something was pushing space apart. That something was named dark energy. It makes up 68% of the universe. We cannot detect it directly. We only see its effects. The leading explanation is the cosmological constant, Einstein's old term, reinterpreted as the energy of empty space itself. But the vacuum energy problem means this might not be the full answer. Alternatives like quintessence or modified gravity remain possible. Current missions like DESI and Euclid are actively testing these ideas. And the final outcome depends entirely on what dark energy truly is, leading to the Big Freeze, the Big Rip, or the Big Crunch. Before we finish, let's clear up some of the most common misconceptions about dark energy. Because a lot of what gets said about it, even in popular science, is not quite right. Misconception 1. Dark energy is the same as dark matter. It is not. These are two completely different unknowns. Dark matter pulls things together. Dark energy pushes things apart. Misconception 2. Dark energy is some kind of exotic fuel or anti-gravity device. It isn't. It is a property of space, possibly as fundamental as the speed of light. It's not a substance you can harness. Misconception 3. Dark energy is pushing galaxies apart like a wind. It isn't. Galaxies nearby, like our local group, are not being pushed apart at all. Dark energy only wins when gravity is too weak to resist. In fact, our Milky Way is gravitationally bound to the Andromeda Galaxy. They are actually on a collision course, expected to merge in about 4.5 billion years. Dark energy won't stop that. Now you might be thinking, this is all fascinating, but why should I care about dark energy? It doesn't affect my daily life at all. Here's the thing. Every technology you use today came from people asking questions that seemed useless at the time. Electricity came from people playing with magnets. Quantum mechanics gave us transistors, lasers, and every computer chip. Understanding dark energy won't change your life this week. But understanding the fabric of the universe, the rules that govern all of space and time, has a way of coming back to us in ways we cannot predict. More immediately, dark energy research is pushing the limits of telescope technology, data analysis, and physics computing. The tools built to study it are already finding other uses in medicine, communication, and engineering. Let's end with the deepest version of this question. Why does dark energy have the value it has? Why is it not zero? Why is it not enormous? Some physicists argue that if dark energy were much larger, the universe would have expanded so fast that matter could never clump together. No galaxies, no stars, no planets. No us. If dark energy were zero or negative, gravity might have recollapsed the universe long before life had time to develop. The value we have seems almost precisely fine-tuned for complexity to exist. This is called the fine-tuning problem. And it leads some physicists to very radical ideas, like the multiverse, where our universe is just one of countless universes, each with different values of dark energy. In most of those universes, the dark energy value would not allow stars or galaxies to form. We only exist to ask this question because we happen to be in a universe where it worked out. This idea, called the anthropic principle, is deeply controversial. Many physicists consider it unsatisfying. It doesn't explain why, it just says we're lucky to be asking. So let's be very clear about where we stand today. Here is what we know about dark energy, with high confidence. The universe is expanding and the expansion is accelerating. This has been confirmed by multiple independent methods, supernovae, the CMB, galaxy surveys, and more. Something is causing this acceleration. It behaves like a property of empty space. It is nearly uniform across the universe. It makes up approximately 68% of the total energy content. The best mathematical description we have is the cosmological constant. When we use it in our models, predictions match observations to remarkable precision. And here is what we don't know, also with honesty and precision. We do not know what dark energy fundamentally is. We have a label, and we have equations. But no physical mechanism has been identified that fully satisfies both quantum mechanics and general relativity. We do not know if dark energy is truly constant, or if it changes over time. The DESI hints suggest it might vary, but this is unconfirmed. And we do not know what the ultimate fate of the universe is. Big freeze, big rip, big crunch, or something we haven't thought of yet. The answer requires understanding dark energy first. What comes next? More data. Better telescopes. Sharper measurements. By 2030, DESI and Euclid will have produced enough data to definitively test whether dark energy is constant, or changing. The Vera Rubin Observatory in Chile will survey the entire visible sky every few nights, cataloging billions of objects. It will track supernovae, galaxy distributions, and gravitational lensing, all to pin down dark energy. We are not at the end of the story of dark energy. We are right in the middle of writing it. Every student learning physics today could be part of the team that finally explains it. Dark energy is not just an abstract cosmological mystery. It is the single biggest gap in our understanding of reality. And closing that gap could rewrite everything, from the structure of space-time to the ultimate destiny of the universe. So next time you look up at a dark sky, remember that most of what you cannot see is not empty. It is filled with something. Something that has been with us since the beginning of the universe, quietly pushing everything apart, waiting to be understood.